Okay, so let's talk about something called thermochemical equations. So up until now, we've talked about a lot of chemical equations, chemical reactions. So essentially what a thermochemical equation is it's just a chemical reaction that includes the enthalpy of the reaction. So remember, enthalpy is delta H given for the molar amounts as written in the equation. So let me write that out. So a thermochemical equation is a chemical equation for a reaction including phase labels, including phases, which also includes the enthalpy change of the reaction for the molar amounts written in the equation. Okay, so let's break that apart a little bit. So here is an example. We're going to say, write the thermochemical equation for the reaction of sodium metal with water. Okay, so sodium metal with water. And I'll go ahead and tell you what the products are, because this is kind of a hard one. I wouldn't expect you to be able to predict the products from here. So write the thermochemical equation for the reaction of sodium water with metal to produce sodium hydroxide and hydrogen gas. And we'll say this reaction evolves 368.6 kilojoules of energy. Kilojoules is going to be the unit that we use for energy most of the time. So we're going to write this thermochemical equation. So a thermochemical equation is a chemical equation including phases, which also includes the enthalpy change of the reaction for the molar amounts written in the equation. So first thing we need to do is we need to write the thermochemical equation, we need to balance the thermochemical equation, and then we need to write what the enthalpy change is. So let's see what we have. We have sodium metal. So that is going to be Na solid, sodium metal, with water plus H2O liquid to produce means there's an arrow, sodium hydroxide. Sodium is Na plus, hydroxide is OH minus. That's one of the polyatomic ions you need to know, hydroxide. I'll just write that. Na plus OH minus, so that's sodium hydroxide, NaOH, this is aqueous, plus hydrogen gas. Hydrogen, remember, is one of the diatomic molecules, so it's H2 and it's a gas. So we've written the equation. Always, when you write a chemical equation, you need to make sure that it is balanced. This reaction is not balanced. It's not balanced because on this side of the reaction I have 1, 2, 3 hydrogens, and on this side of the reaction I only have 2 hydrogens. So I know I need to balance this somehow, so I'm going to give this a 2 Again, when you learned how to balance chemical equations, one of the ways to do it is to take the most complicated compound and increase that by 1 and try to balance everything else. So I'm going to choose this one, sodium hydroxide. I'm going to give this a 2 and then try to balance everything else. So now I have 2 sodiums, 1 sodium, so I'll give this a 2. So 2 sodiums, 2 sodiums. I have 4 hydrogens now. So if I put a 2 here, now I have 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. Now it's balanced. So this is important because remember, we have to have the correct mole to mole ratio. This is a 1. Anytime you don't see a number there, that means there's 1 for the chemical equation. So right now this is a chemical equation. To make this a thermochemical equation, I need to include the enthalpy change. And this reaction says it evolves. Remember what evolves means. Evolves means that delta H is a negative number, 368.6 kilojoules. This is a thermochemical equation. It would look just like this. It would have the chemical reaction written out, and then it would have the enthalpy change at the end. Delta H equals negative 368.6 kilojoules. So this amount of enthalpy change, this tells you this is an exothermic reaction. This means heat is being evolved. It means heat is being given off as this reaction happens. What is true is if we reversed this reaction, so let's just write this for example. Let's say we're going to reverse it. I'm just going to write this totally backwards. So 2 sodium hydroxide plus 1 hydrogen gas produces 2 sodium solid plus 2 water liquid. So this is the reverse reaction. When you reverse the reaction, you change the sign of the enthalpy change. If you were to double the reaction, if you were to multiply all these coefficients by 2, you would multiply the enthalpy change by 2. The enthalpy change is for this reaction at these molar amounts. So a thermochemical equation, it is a chemical equation for a reaction including phases, which also includes the enthalpy change of the reaction for the molar amounts. So this is how much energy is evolved when 2 moles of sodium react with 2 moles of water to produce 2 moles of sodium hydroxide and 1 mole of hydrogen gas. That is important. It's important that you understand that this amount of energy that's being absorbed or given off is for each of those amounts. Okay, so let's look at another example. So same thing. I'm going to write the equation from a word problem and then we'll go through it. So it says sulfur, and elemental sulfur is actually S8. I wouldn't expect you to know that. I would give you that. Burns in air to produce sulfur dioxide. The reaction evolves 9.31 kilojoules of heat per gram of sulfur. Write the thermochemical equation. Okay, so what are we going to do first? The first thing we're going to do is we're going to write the balanced chemical reaction, and then we'll go from there. So it says sulfur, S8, burns in air. Anytime something burns in air, that means you're adding oxygen to produce sulfur dioxide. So we did this back in 161, the types of chemical reactions lab. We talked about burning things versus heating things. And anytime you burn something in air, that means oxygen gas is a reactant. So if I'm to write this chemical reaction, I would write sulfur, S8, which is a solid, plus oxygen, O2, gas, produces sulfur dioxide, which is also a gas. So that's the chemical equation. First thing you need to do after you've written the equation from the word problem is you need to make sure it's balanced. Well, it's not, because I have 8 sulfurs on this side and only 1 sulfur on this side. So I'm going to give this an 8 because I know I have to have 8 on this side. So now let's see if we can balance the rest of it. 8 sulfurs, 2 oxygens. 8 times 2 is 16 oxygens. So I must need an 8 here. So now it's balanced. So this is the balanced chemical equation. So now what we need is we need the enthalpy change. Well, it says it evolves. So that means delta H is going to be negative. But this is kilojoules of heat per gram of sulfur. And that is not what goes here. What goes here is the molar amounts. So I know that this delta H is going to be a negative number, but I don't know what it is yet because this is per gram of S8. And we don't have a gram of S8. We need, what needs to go here is it needs to be per mole of S8. Per 1 mole, because this is a 1 here. So what needs to go here in the thermochemical equation needs to be a 1. It needs to be whatever the coefficient is. If this reaction read differently, it doesn't, but let's just think for a second. If it said it evolved 9.31 kilojoules of heat per gram of oxygen, then what we would need to go here would be how much heat is evolved for 8 moles of oxygen. Not 1 mole, 8 moles, because it's whatever the coefficient is in that balanced equation, but that's not what the question says. So we know we're just going to use this as a conversion factor because it says 9.31 kilojoules of heat per gram of sulfur. So I'm going to say 9.31 kilojoules per 1 gram of sulfur. And I want to convert grams of sulfur to moles of sulfur. So to go between grams and moles, I'm going to use the molar mass of sulfur. Not just sulfur on the periodic table, S8. So the molar mass of sulfur times 8, and I want grams up top, grams of S8, moles of S8. I want grams on the top so they'll cancel with grams of S8 on the bottom. So whatever the molar mass of sulfur is times 8 ends up being 256.56 grams of sulfur per 1 mole of sulfur, S8. So now again my unit is going to be kilojoules per mole of S8, which is what I want because there's 1 mole here. So when I do this, I get in kilojoules 2.39 times 10 to the third kilojoules. Or you could say 2,390 kilojoules. These are exactly the same. What's important is that you have the correct number of significant figures. This number here that's given to us in the problem is the only place for us to determine significant figures from. This number has 3 significant figures. This number has to have 3 significant figures. Both scientific and standard notation here have 3 significant figures. This 0 at the end of a number with no decimal places is not significant. So this has 3 significant figures. This has 3 significant figures. Either of these would be equally correct as long as it has the correct unit and the correct number of significant figures. Also, because it told us that the reaction evolves this much heat, this is not just the answer, the number. When you're talking about thermochemistry, you have to have the math correct. You also have to have the sign correct. Evolves. If you answered 2.39 times 10 to the third on a test, that would be wrong. you would get some partial credit, but it would not be totally correct because you're telling me that it's a positive number, and it's not, because this reaction is evolving this much heat. It's an exothermic reaction. So delta H is negative 2.39 times 10 to the third kilojoules. So that is an example of writing a thermochemical equation. Let's look at one more example while we're right here. So this I said before that you can manipulate this, and whatever you do to the reaction, you also do to the enthalpy change. So let's do one more problem here from what we've been working on. So let's say with this same problem, let's say write the thermochemical equation for the dissociation of 1 mole of sulfur dioxide into its elements. Of 1 mole of sulfur dioxide into its elements. So this is the equation that we have. Sulfur plus oxygen gives us 8 moles of sulfur dioxide. This equation is asking the dissociation of sulfur dioxide into its elements, meaning sulfur dioxide is the reactant and it's breaking apart into this, and it's 1 mole. So essentially what I'm going to do is I'm going to reverse the reaction, and I'm going to divide it by 8 because I want 1 mole of sulfur dioxide. So in thermochemical equations, this is where you're going to see some weird stuff that you've never seen before with coefficients. Up until now, you've only seen coefficients be whole numbers. Sometimes in thermochemical equations, you're going to see some fractions. And this is not something that you've seen before, but I'm going to show you an example of what this looks like. So I'm reversing the equation because it's the dissociation. Instead of forming sulfur dioxide, now I'm breaking it apart. So SO2 gas, and I'm dividing everything by 8. So I've divided by 8, so now this is 1 mole of sulfur dioxide gas, is going to produce 1/8 of a mole of sulfur plus 1 mole of oxygen gas. So this is weird to see this, 1/8 of a mole of something. And this is only when we are dealing with thermochemical equations, because this, we want the dissociation for just 1 mole of sulfur dioxide. So whatever we do to the equation, we also do to the enthalpy change. So here, I reversed it. If I reverse the reaction, that means I change the sign, change the enthalpy sign. So now instead of this being negative, it's going to be a positive number. This was an exothermic reaction. This is going to be an endothermic reaction. I reversed it, and I also divided it by 8. So 2.39 times 10 to the third divided by 8. Remember, I still need the same number of significant figures. I still need 3 significant figures. So it's 298.75. I'm going to round that to 3 significant figures. It's going to be 299. So positive 299 kilojoules. So whatever you do to the reaction, you also do to the enthalpy change. So from this reaction here, I wanted to know the dissociation of 1 mole of sulfur dioxide. So I reverse it. So now sulfur dioxide is a reactant, and I want 1 mole of it instead of 8, so I divide by 8. So we're able to manipulate thermochemical equations. Whatever we do to the equation, we also do to the enthalpy change. Making sure that you're paying attention to the sign of the enthalpy change, because that tells us the direction that the energy is flowing. Is it going in or out? Is it endothermic or exothermic?